Hey folks, welcome to High Performance LLMs First Principles. That's session 6. So again, trying to think of how to achieve high performance for LLMs. And really, this week we're ready to start tying pieces together. So it's going to be end-to-end training, really measuring performance, getting all the things working in a multi-chip setting. So as always, program, predict, profile. Come raise your hand with questions. And then really from a perspective of session 1, I wanted to go through really the pieces we're missing. So we didn't do attention, positional encoding, didn't JIT. There's a little like nuance to the way we were doing data loading is pretty important. Our computations were single chip, and we didn't ever figure out if our MFU was high. So that's what we're going to cover today, really taking the things we've learned in the past 5 sessions and applying them to the basic LLM we coded up in session 1. And then the next session, we're going to do the same, but for inference, hopefully showing a little LLM babbling reasonably efficiently to us. And that's all I had in my planned arc for these sessions. So please do post in the Discord, ask questions. Love to cover more if people have more questions. Cool. So add attention. Okay, well, this one's actually a freebie. Nothing to talk about from a science perspective. Let's just try and program this. So I'm pulling up my entire screen. And what I really just want to highlight is that I am starting exactly where we were at the end of session 1. So this is just continuing session 1, where we left off. Not too much is going on. I'm going to command plus a couple times. I know people need to be able to see. Please let me know if you see anything, but just to remind ourselves where we were, we had a basic loop, collecting data, doing input, collecting outputs, doing gradient updates. We define a very simple model, our model. And then finally, we have there's a little bit of machinery related to data loading. All right, so now I'm going to just jump in and add attention. And it's really exactly what we saw in the previous session. Maybe I'll just copy even the implementation we did during session last time. Cool. And just so you know, Sky isn't on the line today, so I need all the help I can get. So if I do anything too silly on the programming side, please do speak up.
Rafi, could you please zoom in, increase the font size?
Is this one okay?
Better, thanks.
If it's still too small, I can go bigger. It's actually hard to see anything.
Okay, thanks. This is better.
Okay, cool, thanks. So, and in attention, we described this operation on the Q's, the K's, and the V's. I think there's a little bit of a question of how do we generate them, and it's kind of a little bit anticlimactic. But the way we generate them is the neural net learns a weight matrix that emits the Q, K, and V that we saw. So this matrix is going to be I'm basing it on this one that was a feed forward to embed, but this one we actually want to be from embed dim to, and to match our nomenclature from last time, it's going to be num heads and head dim, and we should probably add numbers there. So I'll go before that crashes when we run it. So we'll say num heads is 4. We can always play this later. Head dim is 128, probably the standard choice these days. Perfect. So now we've made a Q matrix. We'll call it QProj. And then all we're doing is saying Q equals, and probably an item is probably clearest here. So we have X, we have QProj. And then we're going to just need to write that item. So let me just write this. So X is BS E, and then QProj is embed head dimension, and then we're just going to write a projection. So this is BS HD. So we're reducing on the E dimension, so everyone's getting divided by the E dimension, and every output is coming with an H and a D. So we'll do that. And then actually the way we're going to get the inputs to this is just by repeating this for the K's and the V's. So the neural net is learning what goes into attention, and then attention is not a learned operation. There are no weights in attention. So the K's come out like this. Oh, typing is hard. And let's get the V's. Okay. And then, well, we actually programmed this last week. So let's just go grab that implementation. I'm just going to legitimately just take this attention. Seems good. Cool. We'll put this into as a function here. And we'll just call attention ourselves. So all this is doing is taking our Q, K, and V and returning for us an O. And then we will learn one more matrix. So okay, so we got to do an out projection parameter. So there's some ways to make this a little bit more beautiful, but I hope it's not too confusing. All we're trying to do here is just very not introduce too much additional concepts, and just go through this. So we now have this out projection. We'll go from num head to embed dimension. And then we are going to have that last Einstein. X, with X is what we started with, is from OProj, O, so this output. And it takes something of O is going to be, based on last time, it's going to be BSHD. This thing we defined to be HDE, and we want to output something of BSE. So we're just shaping our activations so they match attention, sending them through attention, and then reshaping them into our desired form. So I guess I should have probably run it before this, but I'll run it now. Cool. And any questions here while we wait for this to hopefully run? Cool. Looks like no questions. So this is exactly the same thing we did last time. Oh, interesting. So in our attention, we had a sequence, and in this case, we called it sequence length. So this is just continuing, basically making the work we did in the first session match the work in attention. I'm really sorry. I have to command -1. I just need this to not wrap. I'm sorry, Susie. Cool. Taking a little long term. Maybe I should make our test example just a little bit smaller, but the whole thing does run. We get some losses. Cool, cool. I'll just make the number of layers just a little bit smaller, so we can make a little bit less long for compilation in the future. Okay, so we've added attention, and that's the first thing we wanted to do. The second one is positional embedding. So this is a really important part of LLMs, and what's going on here is that the attention operation that we defined last session is order invariant. So the way I think of that is Brown sees the and quick. So if we're doing the Brown here, that word sees the and quick, but it doesn't actually know the order. So the way we solve that in LLMs is actually let the LLM learn its own way of representing order. And we're going to do that by adding an embedding vector. So it's a learnable weight that the neural net adds that is position aware. So at this point, we've created something of batch by sequence by embed. And then the easiest way to do this is we can just do create a positional embedding. And then we want this to always be the same, regardless of what batch you're in. But we're saying each sequence length gets its own position added, and it's embedding that. So we'll call this positional embedding. And then we can call this one positional embedding. And it's as simple as writing x plus equals positional embedding is allowing us to let the neural net add information of its own choosing to allow it to distinguish between the different words. So now it can add some indicator as this vector to be like, okay, this word has some special marking. That's the 0th word. And this word quick has some special marking. So then when we do attention, when we do other operations, we're able to distinguish, oh, this is the 0th word, this is the first word, and so on. Cool. So there's actually a lot of literature nowadays on how to do this. I think the most prominent form is called ROPE, rotational positional embeddings. This idea that we're doing here is a very, very simple, very, very early idea, but perfectly practical. Cool. Let me hold here for questions. Anything else on folks' minds? Anything we should like slow down on? What would be helpful? Okay. JIT. So we actually hadn't yet learned about JIT. So we weren't even jitting the forward pass when we did this in session 1. So let's go through and let's take a look at this and think about how to jit the forward pass. Okay, so you can see this whole shebang is now running. So the jitting the forward path actually comes with some interesting complexity. So first of all, what does it mean to jit the forwards pass? Okay, so there are a couple different things that are going on. The forwards pass is really these two operations. This is what people mean by the forwards pass. We're talking about value and grad on calculate loss. So figuring out the value in grad and then applying the gradients. So the first thing we should probably do if we want to jit the forwards pass is to make a single step. So we'll make this thing. So we'll call it step, and we'll take our inputs. So we'll take we need state. So I think we could get by with state because state.params and state.apply gradient. So that you take a state, you can take a model, you can take inputs, you can take outputs. And then eventually at the end, it has to return. We probably want to know a loss and a new state. So we can return loss, comma state at the end. And then eventually what we're going to get to is going to be loss state equals step, state, model, input outputs. And we can just now piece this all together. So we'll copy this over here. We will copy this apply gradients. So now we've moved these into a function. And then hopefully it's going to be as simple as now we just have to mark this function as being jitted. And that should allow us to jit this computation. We will see how that goes.
You might need to mark the model as static, Rafi.
Sorry, we'll have to map a few things as static, but I haven't yet actually jitted it. Right? So I think I'm okay still. Is that?
Yeah, you just in the JIT. Everything looks fine so far.
Oh, everything. Yeah. Okay. Thank you. Yeah. So we can do it here. We can do it however we want. Jax.jit, and then as was pointed out, a static argnums equals 1. I believe that's the only one that is static here. So that is saying to think about that as being outside of the JIT. You don't have to trace those computations. It's just you can think of it as being a global variable or being part of the function, as opposed to something that's dynamic each time it gets passed in. So
sorry to interrupt. We might need to assign that to a variable though, rather than decorating it and then calling it immediately.
What?
We just might need to decorate, like pass the function through JIT rather than passing it through and then calling it immediately.
I mean, definitely we could do it either way. It might be
Oh,
clearer
so
the way you described, but this should work, right?
it'll work. It just won't cache the compilation, as far as I know.
Oh no, it should cache the compilation.
Oh, really?
Yeah, yeah, we can make it clear. Yeah, that's should not be the case. I guess I should now, since you've raised the topic, I should probably just do it the way that you're worried about.
Sorry to derail.
No, not at all. I appreciate the question. So this is a really important detail. So basically, there are some mistakes you can make. There's some sharp edges and jacks where if you do things the wrong way, Jax isn't able to realize it's already done this computation, and it might do it again. So here, okay, I see. You're concerned that we're going to expose tracing. It's actually not a huge problem here, but yeah, I think you're totally right. Let's do it the way you said. Okay, we'll do static step. So yeah, I think what you're worried is that we would expose. Yeah, it's really not a problem. But we'll do it like this. Okay. So there's some sensitivities there. Really, if you hit them, you'll see it in a profile. Is probably the best way to debug it. Wouldn't be a problem here, but this is a little cleaner. So thank you for the advice there. Cool. So this is now we have now a jittered computation. So we've compiled the whole computation to fit inside of a single program on the kernel, which is great news. Let's go through, see what else I have on my list of things that we're missing here. Okay, this one's really funny. So overlapping data loading. So I forget who said this, but someone in class was like, "Oh, it's laying track faster than the train rolls." So that's exactly right. So the naive solution is that we process step 0, load the data for step 1, process step 1, load the data for step 2, and so on. The better solution is this overlapping. So we do process step 0, then we load the data for step 1 at the same time, and we do it like this, right? So that obviously takes less time. And it actually means you actually really don't care about how long it takes to load the data. It doesn't really matter. As long as you load the data faster than you can process the steps, you don't pay for that time at all. It takes the same amount of time. And obviously, you can see that if we wiggle the load data time, it takes the same amount of time to process the steps. This is surprisingly easy to get wrong by accident. I think we'll actually see in the example that we are doing right now, I have broken it by mistake. So it's an interesting sharp edge. I think we can see that one together. And then just to highlight, this is not a panacea. So eventually, if loading the data becomes too slow, this obviously, you overlap slow steps, totally possible thing to have happen. So just want to highlight that, and then you care a great deal because every second you spend loading data, you are idling the system. So the reason these can always be overlapped in practice is because the CPU is always doing the loading of the data, and the TPU is always processing the steps, or the GPU is processing the steps. So it's they can be always done in parallel, and we should be able to get this nice overlap picture. So there's actually an interesting thing where I believe I have broken this. So let's just start by adding a time. So last step time equals date time, like time. We have a print here, and then new time equals time, and then we can print out as a time elapsed. So we'll need this also to measure our performance later. New time minus last step time. Okay, and then we can print this out. So this will tell us how long elapsed each step. I'll remember to import time at the beginning so I don't error out. Cool. And we get time elapsed in seconds. New time minus start time. Perfect. So this should allow us to see how long our steps are taking. And there's actually a really interesting thing. What? I think I didn't save after importing time. There's a really interesting thing. And if you think about how this code is going to run, after we do static step, we have to execute this print before we can go up here, because we're saying I want this printed, and printing this print requires knowing the loss. So we aren't able to. Sorry, let me get back to the question. I appreciate the question. But the little bug here, I should have just gone with new time. Excuse me, last step time equals new time. And then we run that, and I will go answer the question. I mean, whoever's asking the question, just feel free to speak right up. Yes, thank you. So the helpfully pointed out the bug. Just feel free to just like hop up live, call it out. Really makes it. Programming is hard. Really appreciate the tips. Okay, so this is telling us that our steps are taking 0.022 seconds. So let's write that down. And there's an interesting thing that I was trying to point out, which is that after we do the static step, we have to eventually print. And then we are not able to start loading the new data until that print has happened. So the one way, there are a lot of ways to try to solve this problem. One like kind of simple way is if we can keep a step in counter. This is getting to be pretty ugly as a way of doing things, but step counter. We can increment the step counter, so step plus equals 1. And then we can just like do this less often. So how about we do if step mod n equals 0. That's a classic. We can run this code. And I believe what we'll see is that we'll get more than a factor. It will take less than a factor of 10 logarithm to do this. And the key observation is actually, well, even though we do 10 times as steps, we've 9 out of the 10 of them we were able to overlap, and just one of them we weren't able to overlap. So this should give us a little bit of a speed up. So I think I named something wrong. 162. Okay, so step. I unfortunately named 2 things. Step. Cool. So again, with the structure we're exploiting here is that we can't. This instruction can happen at the same time as this instruction, but if we insert this print, we are not able to progress from line 178 back to 168 until the loss is actually materialized. Okay, so you can see this. So the previous one was 0.022. This is 0.142. So we've made 10 times more compute, and we've got actually a fairly significant speed up here. So that's 0.142 over 0.22, and it's actually like a big speed up. So the one thing I would just mention is like you won't always actually get that big a speed up. It just depends on how things are set. And one really important detail is as you grow the size of your model, you're growing the length of process step 1. Actually, loading the data doesn't depend on the size of it. So you get a smaller percentage speed up for a big model and a bigger percentage speed up for a small model, just because the ratio between this green box and the red box starts to change. Another detail I just want to mention is that like you may remember the data pipeline we made in session 1. It was not the best data pipeline. Right? Lots of like Python, lots of very twiddly bits. It's going to be very slow, but because of this trick, because of this overlap trick, it means we really aren't paying for it at all. Right? We were seeing that basically this was telling us the step time was 0.014 seconds, and then the load data was actually 0.08. So we've actually done this thing fully overlapped. So pretty cool trick, pretty easy to mess up. As you see, the code that I already wrote was doing this wrong. But just I don't have any tip for really making it auditing other than looking at a profile or reasoning about it. Or, I mean, just one more thing you can do is instead of is time repeated calls with the same outputs here, and that gives you a very clear control because you're able to just keep running the same the same loop again and again, and you're able to to isolate data loading and time static step. So there are a number of ways you can solve this problem, but just a good thing to be on the lookout when you start optimizing code, getting that data loading always overlapped. Yeah, come on in.
I was just curious if we could dynamically switch the control flow, like if we run an experiment, for example, for one step and compare these numbers and change the control flow dynamically, depending on the ratio. Because like if we change the kind of data, right, like this would skew the ratio.
Yeah, I mean, it's kind of like always possible. And I think that's like a great point, but it's always possible to do the right thing. So I don't think it's so important. As long as you're overlapped. So let's look at this. So as long as we're overlapping one step with one piece of data loading, but there's nothing else to overlap, and once we do that, we're pretty happy. So I think that maybe my advice would be to always do the right thing, and then I think you should always be happy. Just so folks know, the way we do the right thing in max text, which is a code base I've been involved in a lot, is we back buffer the loss. So we take a step, we get whatever metrics, including loss, we want out, and then we publish them after the next step completes. So we always operate one step behind. So, or you can think of it as we process only after we've dispatched step one do we process step zero's data, or post-process step zero's data. So there are a lot of ways to solve this. Does that help, Sadie? And generally, they should be trade-off free. Typically, there should be no cost to doing the right thing. Cool. Yeah. Any more questions?
I had one quick question, probably just related to the JAX flow. At what point will Python execution block on the device execution finishing? Is it only when you access the loss?
Yeah, only when you access the loss. So printing is accessing. So that'd be like having control flow based on that would break this. Trying to get it out of JAX in some way. And then otherwise, JAX will just happily queue up the various computations you want, and will only block once there are enough computations queued.
Okay, thank you.
Cool. I think that's similar to PyTorch XLA, John. Is there a difference there?
Oh no, it's pretty similar.
Cool. Any other questions here?
Could we click back one more time about the way we were defining the JIT function, like defining it ahead of the usage?
Let's like do this one. First of all, let's decide if this one matters. Okay. So before we debate that, let's decide if this matters. So 0.142 seconds, right? So I think the question, which was like a really good question raised by Zach, if I recall correctly, is that the alternative way we could do it is like this. Does that different approach make sense to you as well?
Right. So basically,
Go on, Nisha.
No. I was saying that yes. So these are the two ways. I'm just trying to understand what difference does it make.
Okay. So let's start by like actually answer that question empirically. So the first time was 0.142 seconds. It's going to be it might be a little bit workload dependent. But let's see how it goes. I believe it should make no difference here, actually. So let's see if that's right. Okay, so I think it probably makes no difference here. These are very similar numbers. There might be a case where it makes a difference if you try to do something sufficiently crazy. I will in the honor of this, like I think really excellent question, I will try to break it. Oh, sorry. Someone has something on their mind. Please do speak up.
So maybe it's being pedantic, but one small difference I imagine would be that if you were to print out how long each iteration takes, iteration number one would print a different number depending on whether you did before the loop starts or inside the loop.
And actually, that is a really good point. It actually isn't really true because the compilation will happen at the first time this calls, because you need to know the sizes. So JAX.JIT isn't actually JITting. interestingly. It's saying prepare this function for being JIT. So really, really good point. The only thing that's changing is whether you call jax.jit, obviously outside or inside the for loop. And the question is what is being tied to jax.jit. So I believe that in this case, it won't realize it's facing the same function repeatedly. So I believe in this case, we'll have made things a lot slower. So I shouldn't have static step. But actually, I believe that in the main case, it will have no difference because it realizes that it's jitting the same function repeatedly. So what I've done here is now I've defined a new function in line each time that Python assigns a new name to, and then this is going to be slow, I believe. But both all the other implementations were all the same, because Jax knew it already had called JIT on this function, and the function had a name. This is really when we need Sky to keep me honest. Cool. So I'm trying to run this. So what I've done now is I've given the function a new name in each loop, and there's no way for Jax to figure out, oh, I've actually jitted this function. To Jax, it just looks like a random function, and then Jax will repeatedly compile. It's going to be slow. Is my hope. And then to answer the question again that was asked is Jax can't actually compile the function without inputs. So this is not really doing much. The action really happens the first time you call it. Cool. Questions? Susie?
Actually, I just want to repeat to make sure I understand. Even if the jax.jit is inside the loop and you're doing the first step, the compilation hit before you're actually on your first step, or you are actually doing compilation during the first step?
It's really during the first step because the compilation can't really happen until there are inputs. Because
Okay.
Jax doesn't know the sizes until it has inputs. So jax.jit is like being like prepare this function for being compiled.
Okay.
And then it's being compiled subsequently.
Okay, that makes sense. So
So
the
I think
first step will be longer than the other steps.
Yes, exactly,
Okay.
exactly.
All right. Okay. Okay. Please.
So I think additionally here, I think people can be rest assured that we have defeated Jax. So now our step times are up to 50 seconds for 10 steps, so 5 seconds per step. And again, the reason for that is now we finally figured out a way to fool Jax. I know, Zach, you raised this one originally. This is a track for you.
Yeah, that makes sense. I just thought that it would have the same problem if you were decorating it in line with the original function rather than the lambda.
Yeah, so the lambda, the problem is it doesn't have a name, so there's no way for it to know, but it knows, it has function equality, so it knows step is unchanged. So it's able, so it can tell.
Oh, well, that's neat. Good to know.
Yeah, go Jax. Okay, anyway, I think that this one that was recommended by Zach is in fact the prettiest. So let's just go with that one. Cool. Any more questions here?
Why do we need the static argnums equals 1?
Okay, yeah, let me think about that one. There's a couple okay, so jax.jit. All right, let me just go to somewhere over here. So what is static argnums doing? So maybe if you think about this function in Python, we have the function a, it takes x, and it returns there's some constant 3. Wow, I did not type well. Then we return constant times x. So what we're imagining here is when we call a, we get 3 times x, right? And the way you're thinking about this probably is the constant that lives here, you could just as easily say it lives here. It's part of the function. It's built into the function. But those are different things, right? The value of a could change depending on the argument. So when we're telling Jax, hey, this is a static argnum, But we're really telling it is just like behave like this is a static thing that can't change, and it is just like a constant of nature. And that makes it easier for JAX to trace the computation if it's making the assumption that that variable is immutable. Otherwise, it would have to be correct if you change the model, and that would limit JAX's ability to do performance optimizations. The model is just like a definition of the math to do, so that is fixed. We aren't expecting to change that. Does that help?
So to make sure I understand, you said that if we define the constant outside and then we specify argnums, static argnums equals 1.
Well, static argnums equals 1 means this is argnum 1, so it's saying model is static.
I see.
Okay, so if like we could just easily like move model to over here.
Yeah.
If we made this change, okay, now it's like, okay, let's just write that down. Okay, 0, 1, 2, 3.
Mm-hmm.
Right, so we have to make this be 3, and then we have to make the other changes you'd expect.
I see.
But what we're trying to say, express the thought, is that this does not change. It's just part of the computation. It's not an input-output variable, but really think about it as being part of the function.
Right. Okay.
And then this can be very important in different contexts. What you could decide to make static and what you can't. And then here it's actually clear that these 3 can't be static because they vary. But in other contexts, it can be an interesting choice. What you compile into the function and what you pass in at runtime. The same way, right, you could, I believe our little sample code, you could make different choices there for your normal functions.
Right. Thank you.
Cool. Happy to help. Anything else here? Lots of great questions. John?
Yeah, this might be another naive JAX question, but is the reason model is static is because the actual model parameters are tracked in state?
Yes.
Okay.
Yeah, model is our model, which is like a representation of this class.
Gotcha. Thank you.
So it has no state. It's just functions. Great question. Susie.
Is there a general rule or like what should we keep in mind except lambda? What other scenarios can break having a JIT
Lambda.
inside the loop? Only lambda?
Only lambda.
Okay.
I mean, I wish Sky was here. This is like Sky's chance to shine, but she's up to that, unfortunately. Cool. Any other questions? Great questions throughout. Thank you, everyone. Awesome. Okay, what's the next thing? I had a couple more things that I kind of missed in our first session. Oh, this one's actually pretty tricky. Multi-chip. Okay, so right now we're just gonna this is a code that we wrote, actually only works on a single chip. So if you think about what we're doing here, maybe I should just throw in a breakpoint. This breakpoint only works on a single. We'll see if we look at what's in params, that everything only runs on a single chip. So we actually need to figure out how to make things run on multiple chips. And I guess there are a couple of things we should do there, but maybe I'll start by poking around and showing us a single chip. So we have params. That's the first object we described. We look at keys. Okay, params, helpfully named params. And then if we look at keys, we have all of these variables we've been defining, and we can just choose one of them and look at its devices only on chip 0. So what we want to do is define this computation so it runs on multiple chips, and we want to do that in a couple different places. So we want to do it for params. Then we're going to want to do, it'll naturally flow actually into train state print. That seems good. And then we'll want to do it for our inputs probably. We probably want those to start out. So let's help make that happen. The best way to do that, or actually, so it's a little bit, I'll say that the solutions JAX offers are perfectly reasonable, but a little bit maybe complicated. So I actually I'm going to look at my notes just for 1 second. Okay, so the way, here's the way okay, let's just discuss why it's hard before we jump into it. So there are a lot of possible solutions that we could do that would work. And maybe the simplest one to think about is like, I could just do a JAX.device put here, right? Right? Well, that solution actually isn't very good. And the reason for that is because I already generated the params, but I generated them on a single device. And if I want to train a big model, it won't fit on that device, and I'm going to out of memory after this device put. So we need to think about how do we do this in a more like abstract way, how do we make the plan, and then we generate the data in the right way. So the way that's you see in max text, I think the way that's the most common in the field is like this. So first of all, there's this JAX.eval shape. And what JAX.eval shape does, it takes a function, it takes in some abstract inputs. Hopefully you can see this. And it doesn't require any flops to do it. So what we're going to want to do is we're going to want to pass in model.init. Excuse me. But we're going to, yeah, this is a little ugly. But functionals.partial model.init only, JAX.eval shape only takes JAX arrays. So what we need to do is pass in model.init, and then we'll put in RNG key here. And now we can put in something of our choice. Our choice inputs here. And we can definitely put in JNP.1s, but probably the more like iconic thing to put in here is a JAX.shape, hopefully it'll help me, D-type structure. So this is a purely abstract thing. I should show that to us here. So where you can just like define this thing, and it isn't actually a real shape. Looks like I have a syntax error. Interesting, too many parentheses. Perfect. So this abstract shape is, it's not an actual thing. It's just like an abstract, like, hey, think about this as being a shape, of array of this shape and this detail. And the reason why that's kind of a good thing to do is it allows us to basically smoke test the system, to run the computation the way we would, as if it was a real computation, but just know what would happen, and not like just talk, like basically reason through what's going to happen without actually doing it. So shaped image, and then we can import functionals. So this is a useful tool to have. Basically, it always allows you to stage out computations that you don't actually necessarily have the memory to do. And again, we couldn't do this initialization normally because at first we don't know what sizes it will be. So I'll just validate that this more or less works. Import functionals. Okay. So now we know that this computation, without actually doing anything, has just run through our initialization routine and figured out the shapes that the initialization is going to be. So now there's like the next trick, which is, all right, so I guess I should take 1 second. I'm going to copy some old code we've done. And I'm just going to create a mesh for us. So like normally this is the mesh we generate. So let's just use the same mesh that we all know and love. Mesh, and then JAX.devices can go here. And then we just need to get an FSDP and tensor dimension here. So we'll say FSDP is 4, tensor is 1. Perfect. So now we have a mesh, and as we generate these weights, there are any number of ways we could do this, but the most kind of iconic way of doing this in the JAX ecosystem is to write NN with partitioning here, and then we put an annotation for how we'd like this charted. So this tensor is embed numheads tensor dimension, and if we remember from previous sessions, the way we typically want this tensor sharded is like this. And we can do this for every weight. We can say, hey, here's how I want it sharded. So let's just go through these, sharding our weights. So I guess I should keep this in with logical partitioning. So these OPROJ goes the same way. And part of why people like this is it allows us to attach our desired sharding for these weights to when we're defining the weights. Cool. So going through here, I think we've got an QKO. So there aren't, I know it actually seems like a lot, but there aren't that many of these we have to do. Now we have to do this one. So this one is feed forward by embed. So we actually haven't covered this one at all, but we'll want to shard this one as tensor parallel FSDP is the kind of the standard strategy. So sharding the big axis, which is the feed forward axis. Okay, and we'll want to do the same for this one. But pivoting it, so we're always sharding the big axis over tensor parallel. And then we will apply this to our additional weights up here. Weights, and then this one actually could really be sharded either way, but we'll just shard it over. I think we can just do this. And we can do this for this one as well. So now we've sharded all of the weights. Normal, and then this one is vocab, so it should be tensor parallel. We haven't actually seen all of the ideal sharding, so we can always play with these. But now, if we rerun the same code that we had before, this with partitioning will actually come through. So hopefully we will see that here. And I'm going to put a breakpoint here so we can reason about the system. So what this will allow us to do is we're providing now model.init will provide us a decorator telling us, hey, actually this one, I want it to be sharded. So if we can choose any of them, all of them are coming out with these little annotations. So this one is saying, well, I want it partitioned. Here's its shape. Here's the D type. And here are the axis names. So this is FSDP and tensor parallel. Okay, so I think now we almost have all of the things we want, but there's basically one last JIT we need to write. So okay, so this is probably a good idea. State sharding equals. So we could write this ourselves, but we're basically saying, given the arrays, the tensors we've created, and our mesh, let's get the sharding. So let's just run that here. Okay. Oh, interesting. So our mesh, I was calling it tensor here, and we're calling it tensor parallel up there. So that's my bad. Mesh, boom. All right, now state sharding. So now all of these tensors now have a named sharding associated with them. Cool. And so this we're saying, well, for this tensor, here's the name sharding. And what's magical about this is now we've like actually solved the whole problem, right? So all we have to do now is say, instead of the model.init, we just do params equals jax.jit model.init out shardings equals state sharding. I think we have to pass an RNG key. And then we have to pass in an argument. So here we can actually do another one of these. And now this initialization is now a distributed computation that we've run before on tens of thousands of computers. So I should probably just make sure it works at all. Because we've JITted this init function. So the point is that this JIT machinery is actually surprisingly useful. So we can see params. Now they're real params, but also if we look for one of them, we should be able to see that this thing is sharded. So keys embed 0, dot value, so that they're this like wrapped state, and then JAX dot debug dot visualize array sharding. I don't quite actually remember the name. I wonder if that's right. Oh, and we see it's sharded. So all we had to do was, this is an incredibly common, incredibly powerful pattern, is stage out the computation as, okay, first run it as an abstract computation. Now figure out what you wanted to learn from that abstract computation, and then pass the abstract computation back into a JIT, and it will do exactly what we want it to do. So now we've actually sharded out this computation, and I think basically now we have a distributed version of this. So we're pretty low on time here. This adventure, we did a lot of things, but covered a bit more time than I was expecting. So I'm not going to try to get to the next one in here, which is actually measuring performance. So I think that'll have to wait until the next one. But I think we've built like all the foundations here. We've been able to get everything working multi-chip, and now it's just a matter of measuring the performance. I think then we'll be in business. Cool. Any additional questions here? Anything that people were interested in? Susie.
I have a few questions.
Yes.
One is, when you have, let's say, 64 devices, how do you pick the optimal mesh? Like, should you have like 2 by 32? Do you need to have 8 by 8? Like, what's the optimal mesh shape that you can use? That's number one question. And the other question is, how do you decide, like, is it better to, let's say you have 2 by 32. Do you want to shard on 32 across the FSDP or tensor parallel? Like, how do you pick what is better?
So yeah, so the kind of like interesting solution, I was trying to cover it in like session 3 or 4, is that like basically the answer is always right for everything to be as square as possible, which is kind of like an interesting, like maybe not obvious result. But the amount of sharding you want, so the output tensors, the tensor each chip gets is as square as possible, minimizes the ICI communications. Secondly, you're kind of hinting at this other thing, which is like, well, like, do I like, if I have if I have a 64, do I think about them as being as 8 by 8, or how do I think about them? And then the answer is there's some, depending on your generation, there are all sorts of different rules. So like on TPUs, V4s, an 64 chip is a 4 by 4 by 4, and therefore you'll want to either have 64 dimensional axis, a 4 and a 16, or a 4, a 4, and a 4. But you'll never want, you will never have an 8 by 8, because physically the system is made out of 4s. Other generations like GPUs are a little bit different, where they could have 8 hosts of 8 GPUs, and there we typically think about it as being an 8 by 8. So the two like high level rules are, you're going to always shard to make things as square as possible, and the dimension set you're choosing depends on your underlying hardware.
And if generation of the hardware changes, how do we move from one sharding to another?
I mean, I don't have a better answer than working it all out, Susie. There's no like cheap answer there, I think.
Okay.
Great questions. Cool. Any more questions? Awesome. Well, great chatting, everyone. Thanks for taking the time. I'm looking forward to planning to wrap things up next week. Let me just show you what I thought through. Oops. Let me Control C there. Let me just show you what so we'll have to cover the backwards pass and how long training should take next week. We'll do some backwards topic, and then there's lots of possible bonus topics. So one we could do is going a level deeper with Shard and Palace. We can also talk about quantization strategies or any number of topics. So please just like post in the Discord if there's something you really want us to follow up on. I'd be happy to do like a little bonus class where we cover up what's on folks' minds. Okay, see everyone next week. Have a good rest of your day.
Thanks, Rafi.
My pleasure.